Hi everyone, this is Wei Chen from PUC-Rio de Janeiro. So today I would like to share with you our recent work about the unification of topological invariants in Dirac models. So essentially what we're proposing is some kind of a universal tool, just like the Swiss pocket knife, as a single formula that can work for any topological invariant in any dimension and any symmetry class. And this work is in collaboration with Shaoran Panatian in Helmholtz Institute in Jena, and also Professor Gerald von Gestorff in PUC-Rio, who is a high-energy physicist of my colleague, who did most of these calculations. I would like to begin with talking about the topology in our daily life. So let's say you have any three-dimensional object. The topology of this object is described by the so-called Gauss-Bonnet theorem, which states that the integration of the Gaussian curvature of a complex surface of this three-dimensional object will give you 4 pi times 1 minus the number of holes that this object contains. As a simple example, if you have a perfect sphere, you know the surface area is 4 pi r squared. And its Gaussian curvature is the same everywhere, which is roughly speaking just the curvature in x direction times the curvature in y direction. So it's 1 over r squared. And as you can see, it's 4 pi 1 times 1 minus 0. So meaning that a perfect sphere does not have any holes. However, there's also another way that you can calculate the number of holes on a sphere. Namely, you can calculate it from the surface normal of this perfect sphere. You imagine that there's a vector field that points outwards on the surface of every point on this sphere, which is described in the Cartesian coordinate in terms of a solid angle theta and phi in this manner, as you know about. Now, if you can calculate the number of holes using this, what we call the cyclic derivative of the surface normal, namely the n dot derivative of theta n cross derivative of phi n. And this way, this formula actually just gives you integration of sine theta. And as you know, that this will also give you 4 pi 1 minus 0. So in other words, you can calculate this topology in this form of integrating the cyclic derivative over the two-dimensional coordinates as well. Now, let's come to the topological materials. So how do you describe the topology of these topological insulators or superconductors in general, at least for a class of non-interacting and low-energy models? They can be described by the so-called Dirac Hamiltonian, where the Hamiltonian is expanded by this Dirac matrices with the components that I call D of K, where K depends on the momentum. So the general feature of this type of Hamiltonian is that after you diagonalize it, you have the spectrum gap that separates the valence band and the conduction band, as described by this energy band structure, and where this Dirac matrices will have to satisfy this Clifford algebra. Now, besides this description, the Dirac models can actually be clarified by the time reversal, particle Hall, and chirosymmetries as described in these manners. And as a result of this classification, here comes this famous periodic table of all the topological materials, where the symmetries will distinguish 10 different classes in this Cartan group theory notations. And according to the dimension from 1 to, let's say, infinity, hypothetically, you can have this topological systems in any dimension. And you see that these topological materials can either be binary, which are the topological invariant, which is analogous to the number of holes of a three-dimensional object, can either be binary, which means that it can only be 0 or 1, or it can be an integer number z, or it can only be an even number 2z. And moreover, this table repeats itself every 8 dimensions. So it's called the periodic table of topological materials. And here, all the classes are distinguished by whether they have time reversal symmetry, the time reversal symmetry squares to +1 or -1, and the particle Hall symmetry, whether it has or it has not, and also its symmetry squares to +1 or -1, or whether it has the chiral symmetry, which is essentially the combination of these two. And you can find this periodic table in many references written down here. Now, without going into too much details, the hand-waving argument is to say that how do you distinguish whether a specific symmetry and dimension can be topologically non-trivial or not? You can ask that, is there some extra symmetry preserved mass term that is allowed in this specific dimension and symmetry class? If the answer is yes, then that means these two different topologically distinct phases are not really distinct, because you can turn on an additional mass term to connect them. And so the system is actually trivial. If not, then the system can be non-trivial, can be integer, binary, or even integer. Now, then you can go ahead and ask, can one double the Dirac Hamiltonian without breaking the symmetry? If the answer is yes, then it means that you can have more than one Dirac points existing in your system, and each one will give you a topological order 1, let's say. So if you have more than one of them, then the topology can be any integer. If the answer is no, then it can only be binary. Now, but if you ask, how exactly do you calculate this topological invariance? Then just by looking at the systems that are relevant to us from 1D to 3D, then there's a big zoo of how you're calculating it. And moreover, each topological invariant actually corresponds to different physical quantities. For instance, showing in this red is this topology so-called Z phase, which corresponds to the charge polarization and some variations, where you take the integration of this so-called Berry connection calculated from the block eigenstate of your Hamiltonian. And it actually takes the cyclic derivative form of this D vector that parameterizes your Hamiltonian. And showing in this purple are these so-called Majorana numbers, which corresponds to whether the system has a Majorana edge states or not. It's calculated from the Pfaff-Young of this Majorana Hamiltonian. And showing in the orange are where you calculate it from the time reversal operator, the Pfaff-Young of time reversal operator, which in 2D and 3D will correspond to the so-called quantum spin Hall effect. And also in showing the red are these Chern numbers where you calculate it from the so-called Berry curvature, which actually in 2D will take this cyclic derivative form of the D vector again. And then finally, in 3D, you have the so-called 3D winding number, which you basically flatten your Hamiltonian and then calculate it in this manner. So you see that there's a big zoo of them, and then all of them correspond to different physical quantities. Now, you might want to ask a simple question. Is there some more unified description of this big zoo of topological order? And it turns out that the answer is yes. Now, first of all, you immediately recognize that there are actually some patterns on this periodic table. The first two classes, A and A3, are the so-called complex series, and they repeat every, let's say, 2 dimensions. They are, at least on the table, they are zigzagging like this. And their topological invariants are all integer. And then showing this blue are the so-called primary series. As you can see, their topological invariants are all integer numbers. And then if you go from this primary series to 1 dimensional lower, then you reach the so-called first descendant, where these invariants are binary. And then 1 dimensional lower, you reach the so-called second descendant, which the topological invariant is also binary. And then finally, you can have this even series where, as you can see, it goes along this, once again, this diagonal direction where the topological invariants are even numbers. Now, it has been known, as you can check in this very nice review papers, that if you, let's say, define a unit vector, which is simply, if you define a unit vector, which is simply the D vector that characterizes the Dirac Hamiltonian, divided by its module, and therefore is a unit vector, and construct a so-called spectrum flattened Hamiltonian, yeah, because it looks just like your ordinary Dirac Hamiltonian, except it's divided by its module. Then you look at these cases that are in R dimension and have a chiral symmetry. Let's say S is equal to 1 and D is in out. Then the topology can be described by this so-called winding number, which is calculated from this Q, which is spectrum flattened Hamiltonian, dQn to the nth power, and then multiplied by your chiral symmetry operators. And on the other hand, if you go to the even dimension and without chiral symmetries, then the topology is described by these Chern numbers, where you calculate it similarly in this manner. And also for the first and second descendants, the binary invariants can all be constructed from these two types of topological invariants according to these dimensional reduction. Yeah. Now, let's say up to this point is very nice. You reduce this whole big table into only two kinds of topological invariants. Now, but if you are a minimalist, then maybe you would like to ask, can we further simplify them? Now, this comes to the work that we recently proposed. Namely, there is, and we will introduce this new topological, or let's say universal topological invariant, which we call wrapping number, that in the differential geometry is also known as the degree of the map. So it goes like the following. So once again, you start from the Dirac Hamiltonian and you construct this unit vector, the n vector, right? And then the degree of the map between the Brillouin zone, which is torus, a d-dimensional torus, and the Dirac sphere that is formed by shrinking all these n vectors into one point, is given by this. That it is nothing but the cyclic derivative of this n of k, in a way very similar to how you calculate topology from a surface normal of the sphere I was showing you earlier. Now, the claim is that this degree of the map is the universal and single topological invariant for Dirac models in any dimension and symmetry class. Now, let me give you an example how this works. Let's consider a lattice model of a 2D Chern insulator, which is described by a 2x2 Dirac Hamiltonian, that is expanded by the Pauli matrices sigma 1, sigma 2, and sigma 3, where the three components of the D vectors are characterized in this way by the two-dimensional momenta, and also by the mass term m here. Now, you can actually visualize what this n vector looks like. Let's say in the Brillouin zone, which is the torus, but I just cut it off and expand it like a square. It will depend on whether this mass term is positive or negative. Let's say for the case of m equals to 1, you will see that if you plot this n vector as a function of what they look like in the momentum space, then you see that they're mostly pointing to the north. Yeah. And the Dirac sphere is formed by shrinking all these D vectors into one point. And then as you can see that it will form a sphere. And because most of them point to the points upwards, so they will become pointing mostly to the North Pole on this Dirac sphere. And in this case, if you use this formula to calculate the degree of the map, then you will see that the degree of the map is actually 0. And meaning that this n vectors is not even wrapping this Dirac sphere once. On the other hand, if you go to m equals -1, and then this m vector in the center of the Brillouin zone is actually pointing downwards. And as a result, if you shrink all these m vectors together, you will see that they distribute everywhere in the Dirac sphere. And then if you calculate the degree of the map, it's going to become -1. And intuitively, this means that how many times the Brillouin zone torus is wrapping around this Dirac sphere is induced by this n vectors. Yeah, for this reason we call it the wrapping number. Now, now you can go ahead and do the straightforward calculation in the odd dimensional with chiral symmetry. This winding number after some algebra is actually, you can actually show that it is equal to the degree of the map that we propose. Yeah, and the calculation is very simple. You just simply go ahead and prove that the integrand in the winding number is actually just equal to the cyclic derivative of the n vector. And likewise, for the even dimension and for the non-chiral case, the integrand in the Chern number after some algebra, you can also show that it is equal to the cyclic derivative of the n vector, which you can also write it as like this, like a wedge product. And also the first and second descendants are equal to -1 to the degree of the map. So now this comes to our main result. Let's say, so all the topological invariants on this periodic table, which once again, it repeats itself every 8 dimensions, can be written in this very nice form that all the topological invariants are just expressed in terms of this wrapping number, degree of the map. Whether it's integer, even numbers, or binaries, they can all be expressed in this universal topological invariant. Moreover, we propose an easy way to evaluate this degree of the map. The procedure is the following. You can choose whatever specific n vector. Let's say the n vector that points to the North Pole. Yeah. And then you take all this momenta that have this n vector point to the North Pole, and then you calculate a cyclic derivative of this n vector at those momentum that have the n vector pointing North Pole. And then the degree of the map is nothing but summing over all the signs of this cyclic derivative over all these discrete momentum points that have this n vector pointing to the North Pole. And according to the formula proposed by Kronecker over 150 years ago. So in other words, you can actually, although it takes this integral form, that this wrapping number has this integral form, but you can actually calculate it on the discrete momentum points. Yeah. And that's it. So if you are interested, please have a look in our, in our paper. Thank you very much.